Hello, I am Yubuzova Khalicha. I would like to report on the ethical high-speed dividing device with the formation of quotient and reminder. Organization of the work. Section 1, Introduction. Section 2 describes a division method to obtain the quotient and reminder using an increased divisor and provides a detailed description of the proposed hardware. Section 3, step-by-step operation of the device using specific examples, illustrating the correct operation of the device. Section 4 includes the concluding remarks. There is a list of sources used. Introduction. Integer arithmetic for digital devices of particular importance because integer is widely used in specialized devices. The most difficult and resource-intensive operation in division and its modification modular reduction. The division operation is crucial for both software processor and digital signal processing devices, machine learning, cryptographic, and arithmetic logic devices. Division and modular reduction are also used in devices to generate finite field elements. Various methods of accelerating the division of integers and implemented hardware allow to obtain high-speed dividing devices with different structures of division device and modular reduction device. Most of these methods cannot be used when working with multi-bit binary integers, since the cost which directly depend on the bit capacity of the numbers used for hardware implementation are very high. In specialized computing devices of a certain type, larger integers with thousands or millions of decimal digits can be used. Therefore, a larger number of research works are devoted to the hardware implementation of high-speed divising devices and modular integer reduction devices of multi-bit binary integers, the results of which are reflected in patents and articles. This article is also devoted to this problem. Purpose and base of the work. The purpose of the work is to develop a high-speed integer divising device for obtaining the quotient and reminder based on the well-known modular reduction device with proven optimal hardware costs and performance. The proposed modification of the known device expands its functionality without loss of performance. Research method. The method used is iterative and is based on subtracting the increased divisor B modulus from the divisor A reducible number. The divisor B is shifted towards the higher digit to the left so that its bit capacity becomes equal to the bit capacity of number A. In this case, the number B is increased by 2 the power of k times, where k equal m subtract g. M is the number of binary digit A, G is the number of binary digit of B. Then the increased divisor B is subtracted from A to obtain the remainder R1. There are no restrictions on the bit capacity of the numbers A and B, except that the bit capacity of the number A must be greater than or equal to the bit capacity of the number B. At the beginning of the operation, the dividing A is considered as a zero remainder R0. On each iteration after obtaining the next partial remainder Ry, the increased divisor B is shifted right by 1 bit. It's reduced by half. If the remainder Ry is positive, then the formed ith digit of the quotient is set to 1, and the reduced divisor is subtracted from the received remainder Ri. If the remainder Ri is negative, the formed ith digit of the quotient is 0, and the reduced divisor is subtracted from the previous remainder Ry minus 1. The received remainder Ri is analyzed at each iteration, making it possible to terminate the operation at any interaction if the remainder is less than the divisor. Most other divising acceleration methods require all divising steps to be performed. Structural diagram of a proposed divising device. The structure diagram contains 4 blocks. Block A is required to synchronize operating of device. Block B is a block of memory for storing divisor B and the increased divisor B. Block C contains the dividend, which is formed as the remainder and stored. Block D is required to form the signal of the end for operating and the result, quotient and remainder. Functional diagram of a device. Present on this slide. The start of device operation is determined by the moment a single start is sent to the device input. When subtracting, the other use the increased divisors in the additional code. With the positive remainder, 1 is formed in the quotient. With negative remainder, 0 is formed. Negative remainder are blocked in and not used. It is necessary to consider action upon receipt of a clock pulse comparison operation as performed on the comp circuit, changes in the state of the counter ST, formation of the next quotient digit in register Q, and a delayed clock pulse. The end of the device operation is determined by the cancel signal, which is generated as the output of the comparison circuit comp if the next remainder is less than divisor B. Results and discussion. Empirical methods was used to prove the correct obtain of the developed device. Considered step-by-step work of device an example of specific numbers in binary number system. Illustrates the correct operation of the device. Consider 2 examples. In the first small example, it took 2 clock cycles to get 4 digits of the quotient and the 7 bits as the remainder. Non-division methods would require 4 clock cycles or higher hardware costs, for example, matrix and pipeline devices. For greater clarity, in the second example, consider operation of the dividing device with the formation of the quotient and remainder when an illustration in both the decimal and binary number system. On the next slide, table shows what will happen in the device when each ICE clock pulse and the ICE delayed clock pulse arrive. The values of the registers A, B, S and the remainder R, Y, the action on the comparison circuit comp and the other at each device and step are given in the decimal number system. Table 1 shows that with the arrival and the delay third clock pulse, the remainder R3 equal 16 from the output of the combinational add is written to register A. The remainder R3 equal 16 and divisor B equal 45 are compared on the comparator circuit comp. Since 16 less 45, the signal cancel is generated. This signal resets the tiger T to the 0 state, prohibiting the passage of clock pulse from the GLC and the process is over. The calculated remainder R4 equal minus 74 will not be used because not the clock pulse and the signal carry equal 0 on the allowed input and 2. The signal cancel allows to remainder R3 from register A to be output to the remainder output, and the quotient from register Q to quotient output. Results and discussion. The division has been performed correctly. Remainder R equal R3 equal 16 as a decimal, equal binary 10000, quotient Q equal 20 at the decimal, equal binary 10100, A equal 916 at the decimal, equal binary 11100101000, B equal 45, equal binary 10101. To calculate the dividend, A equal Q multiply B plus R equal 20 multiply 45 plus 16 equal 916. This example demonstrates that it took 3 clock pulses to form a quotient with a remainder. When dividing by the method without storing the remainder, which requires minimal equipment costs, it would take 5 clock pulses since the bit capacity of the quotient is 5. The purpose, methods, and the device for its implementation can be compared with high-speed division with simultaneous determination of several bits of the quotient, which requires k plus 1 dividing p clock cycles to perform the division operation, where p is the number of simultaneously determined bits of the quotient. The larger p, the less of clock pulses are required, but the more additional circuits to simultaneously generate multiples of the divisor are required, and more than p additional comparison circuits. This method cannot be used when work with multi-bit binary integers, since the costs, which directly depend on the bit capacity of the numbers used for hardware implementation, are very high. Conclusion. In the developed dividing device, the formation of the quotient and remainder occurs simultaneously, and the division time depends on the ratio of the values of the dividing A and the divisor B. If the quotient is equal to power I, that is only in the ith digit of the quotient is 1, then to obtain the quotient with a remainder, it will take I of clock pulse. If the quotient has 1 only in the most significant digit, then to obtain the quotient with a remainder, 1 clock pulse will be required. The minimum number of clock pulses required to obtain a quotient with a remainder is 1, maximum as k plus 1, where k plus 1 is the number of written bits, and whereas it takes clock pulses to get the result. Reducing the number of clock pulses, then operating the presented device is activated by comparing a remainder and revision time does not increase. The known modified to expand its functionality while maintain performance. The increased hardware costs are minimal. Counter, decoder, quotient, register, delay, element, logic circuits, and the results in dividing device it optimal from the point of view of hardware cost and can be used to speed up the operation of dividing integers in systems with minimal hardware cost. Thank you for your attention. Certainly others.